I've graded your second homework assignment. I forgot to bring it to the class today, but the grades are on Blackboard. And as I explained last time, I accidentally labeled the column for your homework 1 to be homework 2. And then I have another homework 2. And I tried to fix it, and I thought I fixed it, but I don't know how it looks like in your computers when you check it in. So if there are 2 homework assignment, columns in your Blackboard grade system, the one on the left is your homework 1, the one on the right is your homework 2. Also, I was going to go through the solution for the third, homework assignment. I forgot to bring the sheet with me again, so we are going to go through that on Thursday as well. And the solution for this quiz, again, I'll go through it on Thursday because the distance students have not taken the quiz yet. Yes?
Do we have class and Thursday?
Oh, I'm sorry. Next week on Tuesday. Good point. Yeah, good. So I'm glad I'm not going to come here on Thursday. So yeah, we won't have a class on Thursday. You can drink as much alcohol as you want. Just remember that power electronics is more important than alcohol, okay? All right, so let's get to our lecture. Do we have any questions? Okay, unless you guys have already started drinking. So what we did last time, we were kind of in the middle of the design procedure for the compensation network. So what we have done so far is we looked at the loop gain, which is this transfer function up here.
I have a small question.
Okay.
What is the use of including zeros in a compensator? Can it stabilize this?
Oh, the question is, why do we add zeros to the compensation network, right? The question is, zeros are good in terms of giving us a phase boost. And I'm going to explain to you what a phase boost is. So zeros are good in a sense that they actually increase your phase, so you can actually provide a more stable system in terms of having a larger phase margin, or having a wider bandwidth. But you cannot keep adding zeros to the system because zeros at high frequencies are amplifying your system, so you are amplifying your noise. So at higher frequencies, you put poles to bring your basic body plot down, something like that. And we are going to see why. And I can show you if I eliminate the zeros, what's going to happen to the... So if you just add poles, you're adding a lot of phase lag to the system, so you're actually making your your loop gain very, very small, so the system gets sluggish. So zeros are like futuristic things. They look into the future. They look at the changes in the system, so they make the system fast. But at the same time, you don't want your system to be too fast, otherwise it's going to go unstable. All right, any other questions? Okay, so the loop gain is on top of the screen. So there are elements in this loop gain that we cannot control. For instance, you step down your output voltage to be able to feed it to your controller. That's like a very simple resistive division, like H of S. Usually the gain is less than 1. Then you have G sub C that we are going to talk about how to design it. And then G of M, which is the modulation index gain, which is 1 over Vm, Vm being the peak value of that triangular waveform. It's usually 5 volts or something like that. And GVD is the duty cycle or control to output voltage transfer function of the particular power electronic converter that you're trying to control. In this case, we are using a buck converter or something like that. So we looked at all of these, and the only remaining piece of the puzzle is G sub C. How are we going to design G sub C? So we had kind of a procedure, we were kind of explaining that. So first thing, before even getting to the controller design, you should make sure that your power stage is designed well, or you have actually a small ripple, a switching frequency ripple in your output voltage or any other signal that you're observing. For that to happen, you have to make sure that omega S, which is the switching frequency in radians per second, is 10 times larger than the corner frequency of your LC filter, something like that. And corner frequency comes from basically this transfer function over here, omega naught, which is this in the buck converter is the square root of 1 over LC. Step 2 was we usually place our zeros of the compensation network. We have 2 zeros, 2 poles, and 1 pole at the origin, the integration one. Make sure that your zeros are around omega naught, which is the corner frequency, like somewhere between 10 times smaller than omega naught all the way to twice the magnitude of omega naught, which is the corner frequency. Then your poles are kind of high frequency poles, so you put them around the switching frequency. So this is guaranteeing that you are actually having a lot of attenuation at that particular frequency to make sure your ripple is not amplified. So for instance, somewhere between the switching frequency and 10 times larger than the switching frequency. So we are going to move on and add more steps to this design procedure. Let me just move to the new sheet. All right. So step number 4 is the distance between our zeros and poles. Our zeros and poles in the compensation network, they shouldn't be too close to each other. So step 4, or 135. Let's do 135 degrees. So what do I mean by that? I'm going to draw it and show it to you, but in general, we are looking at our poles should be like 10 times larger than our zeros. Okay. So what do I mean by a phase boost? So if you look at our compensation network, as I said, you have the integration. First is your pole at the origin. Then you hit omega Z1, for instance. Then you hit omega Z2. Then, for instance, omega P1. And then omega P2. Okay, so this is generally what it looks like, unless omega Z1 and Z2 are identical, so it might look a little bit different. So this is the magnitude. Now here we only care about the phase. For this criteria, we only care about the phase. So if you look at the phase shift or phase delay, so you have a pole at the origin, so your phase starts from negative 100 and negative 90 degrees. Then you hit basically 2 zeros, so your phase should actually increase. And then you hit 2 poles, so it has to go back to negative 90 degrees, something like that. So by phase boost, I mean this much. Because this G sub C is going to be multiplied by the other elements in your loop gain. In other words, the phase of G sub C is going to be added to the phase of the other components in the system. So if you add some extra phase boost over there, that means you are actually providing a larger phase margin for the overall loop gain, something like that. So if your zeros and poles are too close to each other, that means they are already canceling the impact of each other. So, for instance, it may look like this. Okay? So you don't get a lot of phase boost. So this means too close. For instance, if your poles are twice or 3 times larger than your zeros, if they are way far away from each other, you're going to get something like, let me get a different color. You're going to get something like this. Okay, too far. But definitely your boost cannot be more than 180 degrees because you only have 2 zeros. They contribute 90 degrees each, so a total of 180 degrees. So not too far, not too close. Just make sure your phase boost is somewhere around 135 degrees. Okay, and we're going to see now. I have a MathCAD file that we're going to actually see what it looks like. All right, so number 5. This is not an absolute requirement, but it's better to have it. basically the loop gain should look almost like a straight line. Okay. So after you have constructed your compensation network, and then you look at the overall loop gain, it should look like something like this. Okay, almost a straight line, and then at high frequency you have a lot of attenuation, so it gets negative very quickly. Usually this is about negative 20 dBs per decade, and this is about negative 60 dBs per decade. Okay, now it depends on if your zeros are identical or different, or are they real numbers or complex numbers. You may end up with a little bit of a kind of a step over here, and then it goes down, or you may end up with a negative step over here, and it goes down. But overall, the idea is your loop gain should almost be a straight line, and then you cross the gain of 0 dBs or 1 at only one point. You shouldn't just go down and up and down and up and down. You know, something like this would not be acceptable. You know, you are here, then you go down, you come back up, you're here, then you go down again. So you have several crossovers, and that's not a good idea. So your loop gain should almost be a straight. Yes, question?
Professor, will that step 4 is good for the zeros which are also on the right-hand side?
Ask the question again.
If my zeros are on the right-hand side,
Okay.
then is the same criteria should be applied even?
Yes. Okay. Okay. So the question is, if you have a converter with a right half plane 0, should we follow the same procedure or not? General answer is yes, but it depends on at what frequency that 0 appears. Usually those zeros are high frequency zeros. So the design criteria should always be the same, almost be the same. Yes. But again, I mean, the problem with this design procedure is you cannot 100% apply to any kind of converter. You have to be a little bit more intelligent about the overall objectives and then follow the procedure, okay? Like your overall objective is to make sure your system is stable and it has a very wide bandwidth, and also it has a very large gain at 0 frequency. Those are the very objectives. Now, if you want to, for instance, design a buck converter, this procedure that I'm writing should be followed. If you're looking at a boost or a buck boost, they have right half plane zeros. You can pretty much follow the same procedure, but sometimes you have to deviate a little bit from it. Okay?
So boost is actually stabilizing the converter at the frequencies at which it is operating, right?
What is the stabilizing?
The boost that is being provided.
Oh, the boost, yeah. The boost is giving you extra phase margin, so it makes your system more stable, or provides. So you always are trading off between stability and bandwidth. So if you have more phase margin, that means you can actually increase your bandwidths.
Does right-hand plane 0 also gives a phase boost, or it will decrease the phase?
The right half plane 0. The right half plane 0 gives you a. Okay, I should remember this, but I don't. I think we had it somewhere here.
It behaves as a pole. That's why I was asking.
What is that?
The right-hand 0 also behaves as a pole in the left-hand side.
Yeah. So does it behave as a pole when you are looking at? Let me see if I can find it. No, before this.
Yes.
That emoji.
We are also discussing AC.
Not here. There was a lecture we were talking. Here it is. So if you have a right half plane 0, what you have on the right hand side of the screen is going to hold. In terms of magnitude, they behave actually like a 0. In terms of phase, they behave like a pole. So, and phase is important in terms of stability, so they may actually mess things up. So you need actually extra boost for those to get rid of those guys, basically. All right, so we are this is gonna be a little bit more clear once I have a numerical example for you guys. So we are almost done with these steps. So step 6. So we talked about the position of the zeros and the poles. We didn't talk about that gain of A, which is just a DC gain. Let me show it to you what I mean. This gain over here. So we haven't talked about this gain. So once you have actually satisfied all 1 through 5, then you can actually increase or decrease gain to provide a certain amount of basically a phase margin. So you have to adjust it basically. Remember, this gain A is just a number being multiplied by your loop gain. So it doesn't really change your phase diagram. Your phase diagram is the same. If A is larger than 1, it is shifting your magnitude body plot part up. If it is smaller than 1, it shifts it down. It's usually larger than 1. Which is a stability requirement. Okay, so always make sure your phase margin is, for instance, larger than 45 degrees, 30 degrees, 60 degrees. These are all acceptable. There's not a magic number for the phase margin. And remember that your effective gain is not just A, because there are other components in your loop that have a gain as well. Effective gain is A times Vm, which is Vref over Vout, times, oh, I'm sorry, that's the sensing network gain, 1 over Vm times Vout over D, if this is the buck part, assuming you're talking about the buck converter. All right. So we can adjust A to be 200 or 2000, and we're going to see what I mean by that. And then number 7 is we have to double check and make sure that our loop gain evaluated at the switching frequency in radians per second is very negative. For instance, negative 40 dBs. This is to make sure that there is no switching ripple amplified in your system. So how about writing switching frequency okay, just to make sure you're not amplifying it. And finally, in a lot of applications, your load is a variable load. Like it could be 2 ohms sometimes, it could be 20 ohms. So you just got to make sure okay, so if you have a load that is variable, you got to make sure you know put some of the numbers that you have for your load in your design, and see if they all working. Okay, they all work. All right, to make things clear, now we are going to take a look at a design example. This is a MathCAD-based file that I've already prepared. I believe it is not on Blackboard yet, so I have to put it on Blackboard. But anyway, we are looking at the design for the buck converter. Let me make it a little bit larger. Okay. So we are looking at the compensation design procedure for the Bach topology. Your input voltage is 48, your output voltage is 12, inductor has been designed to be 220 micro, the cap is 10 micro, and your load is 5 ohms, constant. The switching frequency is 75,000, and omega s, which is 2 pi f, is about 500,000 basically. The corner frequency is about 20,000, and the quality factor is about 1, and this is our just output kind of impedance, which is the impedance of the L and the C and the R. This is just to make sure your basically power stage is designed well already. So at our switching frequency, which is about 500,000, you should have a lot of attenuation. We already have. You can see you can have about negative 40 dBs or division by 100 of attenuation. All right, the duty cycle is 0.25. VREF, hypothetically, we have, for instance, purchased a chip, and the reference voltage that the chip is providing to us is this weird number of 2.45. So our sensing network has a gain of VREF over Vout. The modulation, the PWM modulator, has a triangular waveform that goes from 0 to 5, so VM is 5. So we have a gain of 1 over 5 here as well. So first we are looking at the control to output transfer function, which is G sub VD. That's part of our loop gain. So it has a DC component, according to that table, is V in or V out over D, and it is 48. And then it has like a second order behavior. So it is something like this. Now I have to make it a little bit smaller so you can see both Bode plots at the same time on the screen. Okay. So you can see the power stage by itself. The crossover frequency is about somewhere between 1 to 200,000 radians per second, somewhere around here. Let's call it, for instance, 3,000 radians per second, 300,000 radians per second. And the system is inherently stable. The Bach converter is always stable because it only has 2 poles. And worst case scenario, your phase goes to negative 180 degrees. So we still have a little bit of a phase margin over here in terms of stability. Now, in addition to what I'm doing, I'm also looking at 2 other. These are not really required for the loop gain design, but I'm just going to observe them to see how do they change before and after the loop is closed. One of them is the audio susceptibility, or how the perturbations in the input voltage would affect perturbing the output voltage. So we have this transfer function from before for the Bach converter. It looks like something like this. So we have a little bit of an attenuation, which is D, basically 20 logarithm of D is this negative number, but it may not be enough. So ideally this transfer function should be 0 or negative infinity in terms of dBs. So it's small, but not as small as we want. So we're going to look at it after the gain is closed. So my candidate for the compensation network is, I have just made my life a little bit simpler. I am assuming that omega Z1 and omega Z2 are equal, and omega P1 and omega P2 are equal. So this 12,000 is gain of A. Then this is 30,000 omega Z1, 30,000 omega Z2, and then 600,000 omega P1 and P2. So remember, for omega Z1 and Z2, the criteria was they should be around omega naught. Omega naught, what was the value for omega naught? Let me remember. Omega naught was about 20,000, yeah. It's about 20,000, so I'm actually making them somewhere around omega naught, basically. So I'm putting my zeros over there, and my poles should be larger than the switching frequency. The switching frequency was about, let me go and check. Omega S is about 470,000. So mine are about 600,000. So I'm going to place them over there. I'm going to delete this because this is what we were looking at last time. Okay. So now we're going to look at the loop gain. Okay, the entire loop gain, all the elements together. So you can see how it looks like. So let me, okay. So on the right, what I have is basically on the bottom right here, over here, what I have is just my compensation network. So I can actually check and see if I'm getting enough phase boost over here or not. The blue one is the phase. You can see as I drew on the screen earlier, my phase starts from negative 90 degrees because I have a pole. I have a pole at the origin, which is the integration one. And then the zeros kick in and it goes to somewhere around here. You can see from here to here is about 90 plus 45. It's about 135 degrees. And then it goes back to 0. In terms of magnitude, actually these are both phase angles. The top ones are the magnitude. The one on the upper corner side, the right hand side, the blue one is just my compensation network. It is similar to what I expected. A pole at the origin, 2 zeros going up, then 2 poles, then going down. Something like that I drew on the board earlier. And you look at your overall loop gain, which is this. So the kind of purple one over here is the control to output transfer function of the buck converter. So these two transfer functions are being multiplied by each other. In a Bode plot, they're kind of added with each other. So these two added with each other gives me the overall loop gain over here, which is the red one. And the angles are also going to be added with each other. So that's why we are actually trying to get a phase boost. Although in a buck converter, it's not that big a deal. The system is relatively stable anyway. So these two are going to be added to each other to form my phase angle. So look at the loop gain. We need a very high gain at 0 frequency or DC frequency. This is to eliminate a steady state error. So we achieved that. Our bandwidths are relatively large. We cannot actually expect, and I'm going to put some other numbers in there to see what it looks like. But our bandwidth is about 30,000 radians per second. We cannot really practically increase the bandwidth beyond that because if I do it, I can actually increase my gain of A to have a wider bandwidth, but at the same time, you don't get the attenuation that you need at the switching frequency. The switching frequency was about, like, let's say 500,000. You can see you're getting about 40 dBs of attenuation. Is the system stable? My crossover frequency is about 30,000. And my phase angle at 30,000 is about negative 135 degrees. So I have actually a phase margin of 25 degrees. So that's also good. Let me make it a little bit smaller and then play around with some numbers. Or let me see if I can do it 60% or 60. Yeah, I think 60 would be good. Okay. So you may come and say, I don't like this bandwidth. I want my system to be faster. And by adding to this gain, I want to actually make our system faster. So instead of 12,000, you may say, I want 120,000. Okay? So now you can see that my magnitude in terms of my phase loop, the red one, is shifted up because I just multiplied by a larger number, and in a larger scale, it is just shifting up. Now my crossover frequency is about a little bit higher than 100,000 radians per second, which is good. The indication is the system is fast, but you can see you don't have enough attenuation at the switching frequency. Okay. But the system is relatively still stable. You still have about 45 degrees of phase margin, so it's good. But again, you're not getting enough attenuation at the switching frequency. It's really hard to make this system unstable because buck converter is inherently stable, but let's go to this even 10 times larger number. And so I keep increasing my gain. Now I have a very high bandwidth, but my gain at the switching frequency is about the same, which is 1, which is scary. And the system is still stable. I'm just having a lot of ripple in my output because I'm not doing a lot of attenuation. I'm going to show you the time domain simulation as well. So let me make this delete these two zeros. Now you may come and say, why did you put the zeros at 30,000? Why didn't you put them at 20,000? So let's take a look at that. 20,000 and 20,000. So we are actually separating our zeros and poles a little bit away from each other. Not a significant thing will happen. You can see pretty much everything is the same. So it's not like 30,000 is the absolute correct number and 20,000 is the absolute wrong number. But, you know, for the sake of, you know, argument, let's make them really small. Like instead of 20,000, let's make them 200. Okay. Now you can see everything is kind of messed up. You don't have a good resolution in this Bode plot over here, but you can see that your bandwidth is actually beyond your scale. So it's a very fast system, but you're also amplifying your switching frequency. I can actually see, we can see that in simulation. And so technically, if you run this, you're going to actually see not a reasonable output voltage. In terms of phase boost, you can see that because zeros and poles are very far away from each other, because I shifted my zeros to the left, I almost get 270 degrees of phase boost over here. And it's a lot of phase boost, but then you are not attenuating your switching frequency. So then you may say, okay, I'm not attenuating the switching frequency. Let me reduce this to get a better attenuation. How about this? Still not enough. So now your switching frequency here, you get a little bit of an attenuation here, but then you can see your crossover frequency. You have 1 here, 2 here, and 3 here. It's kind of a little bit messy transfer. Remember, it was supposed to look like almost a straight line. It doesn't. So that's not a very good design. So let me go back to 1200 and then 30,000. And then you may come and say, was this the original design? Was it 12,000 or 120? 12,000, yeah. You may come and say, how about, why did you put these poles at 600,000? What about 700,000? It doesn't really make a huge difference. But if you move them way to the right, again, you are going to get a large phase boost, but you don't get a lot of attenuation at the switching frequency. All right. So this was all about the loop gain. And remember, your audio susceptibility or line to output transfer function, as well as your output impedance transfer function, when you close the loop, all of those new transfer functions will be the original transfer function divided by 1 plus d. We had it somewhere earlier in our notes. So now you can see that if I do not close the loop, the red one is my audio susceptibility. If I close the loop because of the division by 1 plus t, the blue one is my new audio susceptibility. And as you can see, like for instance, if I have a ripple of 120 hertz in my, for instance, input voltage, you're attenuating that 120 hertz a lot to appear in the output voltage, which is very good. So you have, the more negative you are, the better it is. So this is indicating that at least at frequencies that I'm worried about, for instance, 120 hertz, I'm doing a lot of attenuation, which is good. The other one is the output impedance. Now, we don't really deal with output impedance in this class, but output impedance becomes important when you're cascading converters with each other. So again, your output impedance ideally should be 0 or negative infinity in terms of dBs. The red one is the output impedance if you do not close the loop, and the blue one is your output impedance after you close the loop. Again, you can see it's smaller, so it's contributing to dragging down your output impedance after you close the loop. All right, so this is all frequency domain design. Now let's take a look at the time domain design. All right, this is the converter that we saw before last time. So it's the buck converter. Input voltage is variable, could be variable. The output voltage could be variable. And I have a bunch of basically suggestions for my transfer function. I'm going to show you the good one first, then we are going to see what happens if we mess it up. So to refresh your memory, let's say we have an open loop system, okay? And our load is constant of 5, but our input voltage is having some fluctuations. For instance, our input voltage jumps from, it has a DC value of 48, but in addition to that, it has a little bit of a ripple of 4 volts peak to peak at 100 hertz. All right, so since the loop is open and you're feeding the system with a constant duty cycle of 25%, you would expect the output voltage to be also fluctuating. And this is how it is. Your output voltage on average it is 12, but it's basically the ripple is 4 times the duty cycle, which is 0.25, so you can have a 1 volt peak to peak ripple over here. All right. Now, if you switch it to the good compensation, because I'm doing an extra amount of attenuation at 120 hertz or 100 hertz, whatever it is, I would expect things to get much better. And let's see. So now my loop is closed. I'm using that very long kind of transfer function as my compensation network. And now you can see you still have that ripple, but it's much smaller. It's only like 50 millivolts up and down. So almost as small as your switching frequency ripple. So we did a good job. So if you just zoom out, it's almost a flat line. Okay, so your compensation is doing a good job. What if instead of switching the load, switching the source, I switch the load, for instance? My load is now variable. On average, it's 5 ohms, but at a very weird frequency of 100 hertz, it's fluctuating to 5.5 to 4.5 kind of ohm. All right. So bad scenario, which is open loop. Okay. First of all, you see that it is not a significant problem. Even if the system is open loop, your output voltage is still around 12. It doesn't deviate much. The explanation is your output impedance at that particular frequency is already small. It's about, for instance, negative 28 dBs negative. So you are making it more negative, which is good, but it's negative to begin with, so it's not a significant contribution. So if I close the loop, I'm expecting this to be get even a better. So this goes to about I don't know, 12.0, for instance, 8 or something like that. Now let's close the loop with the giant transfer function. So it got a little bit better. Even at this scale, you don't even see the variations of the load in the output voltage. So you're doing a good job in terms of load regulation. So again, the explanation, I'm even providing more negativity in my closed loop output impedance. So it's less sensitive to the variations in the load. What about bandwidth? So let's take a look at the bandwidth example. Instead of having now all of a sudden, for instance, I want to change my load from 4 ohms to 4 plus 2, and then come back to 4. So you jump from 4 to 6 and then come back to 4 to see what happens to your output voltage. Ideally, your output voltage shouldn't even see anything. It should be an absolute constant. So first, I run it with a constant duty cycle. Okay, here the duty cycle is constant. Open loop behavior. You can see you observe a spike. Your output goes from 12 to as high as close to 15, then kind of recovers back. And then when it jumps from 6 to 4, we almost see a similar behavior in the negative territories or below 12 territories. Now let me close the loop this time. So now the loop is closed. That transfer function is in effect. And now it got a little bit better, not significantly better, but a little bit better. All right, instead of going to 15, now it only goes to like almost 14, which is a little bit better, but not much better. The reason is If you look at your bandwidth before and after adding the compensation network, there's not a significant extra bandwidth that you're providing. Your bandwidth is kind of limited to your switching frequency, because switching frequency is hovering around 500,000. You need good attenuation at that 500,000. So your bandwidth cannot go beyond this point. Even before, you were almost around that. So if you look at like GVD, you are almost in that vicinity anyway. So before and after, the bandwidth doesn't change much. So in terms of your system getting faster, it is not a significant change. But let's say you get greedy. You keep increasing this gain in order to increase the bandwidth. For instance, let's just even go to a normal case. Let's just have a change over here. Let's say instead of 12,000, the way I did in the mathget file, go to 1,200,000. So now you can see the system is all over the place. It's a little bit chaotic, so it's really not stable. The funny thing is, you can see that overshoot is gone. So it really reacts very quickly to that overshoot. But the problem is you don't really have a good steady state behavior. So this is what we saw earlier. I just increased this number to something that is 100 times larger. And, okay. So you can see everything moved up in terms of my loop gain, magnitude of my loop gain. Now this is my new bandwidth. It's much wider, but I don't have a lot of attenuation at the switching frequency. So this is kind of what we expected. Let's do another thing, and that would be, for instance, let me bring it back to 12,000. Remember, we put our zeros, we place very small zeros, like for instance, instead of 30,000, let's put them at 30. All right. Okay, unfortunately, we haven't even reached the steady state. All right, first of all, the output voltage is not what it is supposed to be. It was supposed to be 12, and now it is a large number. I think something is being saturated here, but nevertheless, you can see this spike hasn't got better either, and it takes a long time for the system to kind of recover. So you can see the output voltage keeps going down. I think I have to run this for a much larger time for the output voltage to gradually go back to 12. So you can see the system is very, very, very sluggish. So very low frequency zeros are not good, and again, the explanation is, we switch it back to 12,000. So as we saw earlier, instead of 30,000, if I just put very low frequency zeros, you get a very kind of a weird looking transfer function. And it is still stable, but as you can see, the system was very slow. So design is kind of an art. There's not one unique solution. It's just a matter of practice, trial and error. Look at the frequency domain response, look at the time domain response, and finally get to a particular point. Now, do we have any questions? So I'm going to post these files on Blackboard. If you guys want to mess around with them, take a look, change a particular gain or change the position of a particular zero and see what happens. Any questions? All right. So this was all about why we need the transfer functions. This is why, because then we have to design the rest of the system or the compensation network. And then what I'm going to do now is, let's say you have gained this knowledge and you really want to build your converter, okay? So I talked about this G of C, the compensation network transfer function, which looks like something like this on a piece of paper. 2 zeros and 3 poles. The next question is, how can I realize this network? How can I basically build this network? So now let's talk about that. All right, this is more like an active filter class now. So you have a filter basically, and you're trying to build that filter. You have two approaches, active and passive, because you need a high gain. Active gains would be better. So hardware basically. So we're going to use an operational amplifier to do this. So going back to, for instance, circuits 2, okay. So this is how you can physically realize your compensation network. You have basically 3 resistors and 3 capacitors. So VC is the output of your compensation network. Vout is either the original Vout or a scaled down version of Vout, assuming that you have a sensing network. So in order to analyze this, you can consider this. Just label this to be the input impedance kind of a network, and this is like a filtering network. So going back to circuits 1, remember we are looking at the gain of this network to be negative. Okay. The term negative, the sign negative, no problem. Remember, we are all talking about negative feedback. There's always a negative sign in the loop, so that is already taking care of that. And ZF is the impedance of the block on the right, and ZI is the impedance of the red block on the left. So technically, ZI is nothing but R1 placed in parallel with a capacitor placed in series with a resistor. And then ZF is nothing but a capacitor placed in parallel with another capacitor, which is placed in series with a resistor. Okay? So once you plug in ZI and ZF, you are going to see instead of omega 1, maybe I should write A. Okay. Now, like, once you do a one-on-one comparison, A turns out to be 1, which is like a DC gain, R1 times C1 plus C3. Omega Z1 is determined by R2 and C1. omega Z2 is determined by R3 and C2. And then let's take a look at omega P1 and omega P2. I'm sorry, the one that I wrote up here is actually omega P1. Okay, omega Z2 C2 R1 plus R3. And then omega P2 is okay. So in terms of dimensions, they're all doing good because they're all representing 1 over RC kind of a thing. And now as you can see, you have extra degrees of freedom. Like it's not like if you know where your omega P1 is, for instance, 600,000, that exactly determines what R3 and C2 should be. So you can select a few of these numbers, using the components that you have in the lab, like a film capacitor, then find a numerical value for the other components. So there is not a one-on-one kind of a match, so you still have extra degrees of freedom in determining the exact numerical value for R1, R2, R3, and C1 and C2 and things like that, okay? So this is what the system, what the network should look like. And again, as I said, don't worry about this negative sign. We actually need this negative sign because we're looking at the negative loop anyway, negative feedback. All right, any questions? Yes?
The overall negative sign is being contributed by just the GC of S. The other components are entirely positive, like for the T.
That's right, exactly. That's correct. Okay. Now, other questions? Okay. So now let's say you have designed your composition network. You know what the elements you need. The question is, how can you basically build the whole system, okay? The good news is there are products out there that directly integrate all the components that you need. So it's just a matter of buying a chip that is only, for instance, I don't know, probably $5 or less. And all of the components that you need are here. Now, there, good news or bad news, there are like thousands of these chips available. So the question is which one you should buy. I don't really know. I can't tell you. You have to be familiar with the fundamentals of these chips, then make a decision of your own. And unfortunately, they are getting fancier and fancier. Like this one is a TI product. It's a relatively old one, TL494, and it has 16 pins. And this is the diagram of the chip. So you can see, for instance, instead of having 2 error amplifiers, it actually has, instead of having 1 error amplifier, it has 2. I don't really know why we need a second one. But anyway, I just mentioned that you have to be able to build this compensation network by adding ZI and ZF networks. So let's say you select error amplifier number 1, and then pin number 1, number 2, and the output, which is output of this amplifier, which is pin number 3, are the same as this one, and this pin. So these pins are available to you. You can actually select your RNC and build them around this part of the chip. Remember, we need an oscillator in our PWM block, right? We needed an oscillator to give us a kind of a sawtooth waveform, ramping from 0 to 5 and coming down. This is the oscillator. And by selecting RT and CT, you can actually select the frequency of these oscillators. So there should be graphs down there somewhere explaining how RT and CT should be selected. Yeah, it's like oscillator frequency versus RT, the timing resistance, and then the capacitor is also another parameter. For instance, if you need your switching frequency to be 100 kilohertz, you can select RT to be around 10K, and then CT should be around about 1,000 nanofarads, something like that. So you can actually select your frequency using these graphs. What else do we have here? Remember, we needed a VREF, a reference voltage. which is thermally compensated, and there is a reference regulator. The job of this block over here is to give you a reference voltage, which is pin number 14. So for instance, remember here my reference is connected to the positive terminal of my error amplifier. Same thing. So externally you have to connect, externally you have to connect pin number 14 to the positive input of one of your error amplifiers, whichever you're using. Now, what is the value of this reference? In my simulation, I assume it's 2.45. Each chip has its own number. You have to make sure you're using the right number. Let me see if I can find it here somewhere. It's actually 5. So it's a very straightforward number. Okay, your reference is 5 volts. What else do we have in this chip? There is a DTC, like a delay time control. I mean, in case you are using, two switches that are complementing with each other, in order to avoid their overlapping, their conduction is overlapping. There is a delay mechanism over there. There are 2 transistors on the output side. You can use these transistors as your gate drivers, or you can use external gate drivers. That's actually your choice. And that's pretty much it. So you need an oscillator, you need at least one error amplifier, and you need one reference. And actually here we have more than what we need. There's another chip, and I'm going to post this on Blackboard as well. There is another chip that I found. There are many of them. This is also a TI product. It's TL 5001. So it only has 8 pins. And this is the diagram. So we only have one error amplifier, this guy over here. And the positive pin of the error amplifier is not even available to us. It is internally connected to VREF, which is 1. So these numbers always change. The previous chip was 5 volts. This is 1 volt. You have to pay attention to that. But these 2 pins, the negative pin and the output of this operational amplifier, is actually available to you. So you still can build your network around it. You only need this pin and this pin. You have a reference. As I said, it's actually providing a reference to you. You have an oscillator. This oscillator does not need an external capacitor. It only needs an external resistor. So again, there's a chart down there telling you that if you select this external resistor to be, 10 kilo ohms, your switching frequency is 100 kilohertz or so, whatever it is. Then internally, it has a kind of a transistor over here. Sometimes you can use this transistor as the transistor of your converter, assuming that you are not processing a lot of power. Or it could be part of your gate driver, basically. And it has some bunch of other features. For instance, again, that delay thing is still here. There is a short circuit protection. There's a lot of protection and fancy features in a lot of these chips that you may or may not need. The short circuit protection, I don't even remember what it is. I mean, if there's a short circuit in the system, it commands this chip to automatically turn off or something like this. Some of them have a block which is called, here it is, under voltage lockout. So it looks at your power supply that you're providing power to the chip. Sometimes the same power supply that is providing power to the power converter is the same power supply that is, so you don't need a separate power supply for your chip. It actually feeds on the same input voltage. Sometimes there is a range associated with that. Like, let me see if I can find it. Well, this is weird. They don't really have the table. Okay, it starts from here. So your supply voltage, this is good news. Your supply could vary from 3.6 volts to 40 volts. So it actually covers a wide range of applications. If you have an input voltage that is 15 or 5 or 24 or even 30, you can just directly feed that to your chip. You don't need a separate power supply. So that's very, very good. But that under voltage lockout is if your voltage is below 3.6, in order to command the chip, don't do anything because the input voltage is too small. They have a block over there to turn the whole chip down. Some of these chips, when you're selecting them, actually tell you that in what range that oscillator functions. Like here, your oscillator functions from 20 kilohertz all the way to 500 kilohertz. That's actually quite good. Usually, you're looking at 100 kilohertz, 150, or 75, so it can actually easily cover that. Also, there is a lot of other information. For instance, your reference, as I said, is 1 volt. This is the under voltage lockout. Below 3 volts, it shuts down. Short circuit protection, there is actually information that the oscillator, the typical value is 100 kilohertz if you use an external resistance of 100 kilo ohms, something like that. Then they have more information about how much current you can sink or source on the output side. If you're, for instance, you're processing 1 or 2 watts of power using your boost converter, you may say, I'm just going to use this switch as the transistor in my boost. If not, then this could be the transistor of your gate driver. If not, you can just actually use this to feed a gate driver. I mean, it depends on how much current you're going to sink or source. All right, any questions? All right, so these are 2 commercially available chips. As I said, there are at least tens of thousands of these chips out there. They're all very cheap. Some of them have so many fancy features. Some of them do not allow you to go beyond, for instance, 50% duty cycle, or only 0 to 50. Some of them do not allow you to go below 50%, from 50% to 100%. Some of them have 2 channels output, 4 channels output, so many features. But I was trying to find the most basic ones that are out there, basically. All right. Since there are no questions, let's move on to a new topic. The new topic is current mode control. Okay, so what do we mean by current mode control? Okay, we are here. Okay. Sometimes it's called current program control. Sometimes it's called current injected control. And sometimes it's called dual loop control. Okay, so there are many names. It kind of was invented back in the 70s. And remember, we are under, our discussion only covers CCM, continuous conduction mode. So the whole topic or idea is we have a power electronic converter. Even in the simplest converters possible, there is at least 1 capacitor on 1 inductor. Each capacitor and inductor by default, by their very basic feature, they are energy storage devices. So they can actually, they have some memory. They are actually like integrators, basically. And if you look at the control from a control perspective, they are representing a state in the system. So the voltage of a cap is one of the states in the system, if you go back to a static space representation. And the current of an inductor is one of the states in the system. What we have learned so far, now that we have a second basically control algorithm, now everything that we have covered in terms of control is called voltage mode control, okay? So what we have done so far is, like for instance, this design that we had, we are trying to regulate the output voltage, which is the voltage of the capacitor, which is one of the states in the system. But we don't even care about the other state, which is the current of the inductor. For instance, if you assume your input voltage all of a sudden rises. If the input voltage rises, ultimately the output voltage rises. And then you realize the output voltage is rising, then it is being compared with the reference, then you have to make correct decisions, for instance, increase or decrease the duty cycle to compensate for that increase in the input voltage. Now, if you're at the same time monitoring the inductor current as well, which is the second state in the system, before even you see any changes, or even faster than you see any changes in your output voltage, first you see that the inductor current is also rising. So then you can actually respond to that change quicker. All right. So remember, if you do voltage mode control, the change has happened. The response of the system to that change has to appear in your output voltage. Then your system starts reacting to that change. In a current mode control, you can actually have a chance to react quicker because you're looking at the current of your inductor before even you look at the voltage of the output capacitor. So if I want to draw a block diagram for it, we are looking at something like this. And by the way, there are many current mode control techniques. We are going to actually mention a few of them, and we are going to analyze one of them. Okay, so let's go back to our classic buck converter. So this time, let me use a power MOSFET. Okay. Okay. So, similar to the case before, we are still measuring the output voltage because ultimately we want to regulate the output voltage. Then we place a compensation network here. Okay. Then before, what we did in the voltage mode control approach, or in the single loop control approach, we would apply this to the PWM block. Now we are going to do it a little bit differently. We are going to compare this with the current of the inductor. Okay. Then we use like a set and reset latch. Then you use a gate driver and then command the gate. And then we have a clock over there. Okay, so in the general case, we may have a sensing gain here too. Okay. So the idea here is treat the output of your voltage compensator as a reference for your current. Before, we were treating that as a reference for the duty cycle. Okay. So if the output of the voltage compensation goes up, treat it as if we need more current in the inductor, and then make decisions to actually increase the current of the inductor. Or if this reference goes down, treat it as a, that means your inductor should provide more current, less current. So you have to make, actions to reduce that. And we are going to have, we are running out of time. We're going to have a bunch of examples next time. But the name dual loop converter, which is still on the screen, comes from the fact that now you have actually two loops. There is a loop here, and there is a loop over there. So that's why we call it dual loop control, or we call it current mode control, because not only we are measuring the output voltage, we are also measuring the inductor current. So we're going to continue this. There is a modeling approach associated with that, and this is what we are going to do next week on Tuesday. So see you guys next week on Tuesday. All right.